So the first part of today's lesson, I know when I first learned about it, I was like, that is freaking genius. The second part, we use a whole lot more. It has a ton more applications, but I remember being really struck with the first idea. So we're going to use the standard deviation as a ruler. Yeah, I know that sounds weird, but we'll use it to measure things, and the normal model. So, a little story. Way back in the fall of 1979, I took the SAT.
Wait, you took it? Or like,
This is my story. This is me.
Okay.
This is for real.
Oh, really?
Yeah. Real numbers, the whole deal. Back in those days, students didn't generally take prep classes, and they only took it once. You took it once, and that was the score you got. Several weeks later, I got my scores in the mail, and I went, okay. I had no idea what was good, right? And so I looked at them and I was like, okay, it really didn't mean anything to me. The same thing actually happened with IQ scores. I got an IQ score from something at some point, and I was like, is that good? I mean, I had no frame of reference. So before I started teaching this class, I actually looked this up. The mean score for math was 493, and for what they used to call critical reading was 505. Those were the mean scores. That has changed since then. All kinds of things have changed about it. College Board gets nuttier every year, in my opinion, but they're the only game in town, so just knowing this information and knowing my score, would that be enough to tell me how well I scored? By the way, I scored a 600 on both parts. Okay? I still am like, but so if you know what the mean score is and you know what you scored, do you know how well you've done? You know that you've done above or below, but you don't really have a sense of how well did you do. Okay? So, what other information might be helpful to be able to compare my score?
you have the percent of it. Now they give you the percent of the 99 percentile.
Well, okay, so I don't want a particular number about how it applies to me. I guess they could tell you what score was the 99th percentile, and you could work backwards from there. But even then, you don't know what the 85th percentile is then. So the other thing I could know is, what's the standard deviation? How many standard deviations is my score above or below the mean? This also allows you, and the thing that struck me about this is, doing this allows you to compare two completely different groups. Let me give you a sports example, okay? Let's say that you are a running back in the NFL and you scored 9 touchdowns in a season. You could find out what the average was for all running backs. Usually you do it for all running backs with more than 100 carries or something like that, so you don't get people who didn't have a chance. And you could find the mean. You could also find the standard deviation. Okay? You could figure out, all right, how many standard deviations am I above the mean? Then you could go to someone who plays baseball and see, how many home runs did you hit this year? What was the mean? What was the standard deviation? And again, usually you say, people who've had at least 100 at bats or something like that. And you could go, how many standard deviations above the mean were you? And I can determine whether I, as the football player, am a better touchdown scorer than that person is as a home run hitter.
Dang.
Because you can't just compare them side by side because it's different things. But once you look at it in terms of how many standard deviations it is, you can compare completely different things. This is also how, and again, I apologize that it's lots of sports examples today, but this is also how you can compare things across different eras. So, for example, today in the NFL, quarterbacks throw for a bazillion yards every year. If you want to compare them to someone who played in the 60s, you can't just compare the yardage and the completion percentage. It just doesn't work. But what you can do is for each of them, you could compare their yardage to the mean and how many standard deviations they were above it or below it. And then you could compare those two across completely different eras.
Right, that is really cool.
Yeah, see, you can
Never
see
thought
why
about that.
I was like, oh, so you can compare against different eras, but you can't do it just with straight numbers. You have to compare them to the people who played in that era.
Wow.
So yeah, you can you can see the look in your eye. You're like, oh, that's a cool idea, because you think about that. You're like, well, how do you compare that? You can absolutely do it.
Way to do it.
Here's how you do it.
Way to go.
What we do is we standardize the value. Now, to standardize the value, what we do is we take the value, subtract it, subtract the mean, and then divide this difference by the standard deviation. And this should say just subtract the mean, not subtract from the mean. So we take the value, subtract the mean, divide by the standard deviation. And what that's going to tell you is how many standard deviations you are above if the number is positive, or below if the number is negative, the mean. This is usually called a z-score. So z-scores measure the distance of a value from the mean and standard deviation. They are unitless, which is also why you can compare completely different sports or completely different anything else's, because there's no units on them. All right, so when we standardize data, we're doing two things. First, we're shifting the data by subtracting the mean. Now, when you shift the data, all of the data gets shifted exactly the same distance, right? So adding or subtracting a constant to every data point adds or subtracts the same constant to the measures of position, but leaves the measures of spread unchanged. So your standard deviation isn't going to change, your interquartile range isn't going to change, your range isn't going to change. All those things that have to do with spread don't change when you subtract the mean from every single data point, because you're just moving all those data points further down or moving all those data points further up. Second, we do change the spread by dividing by the standard deviation. Now, the standard deviation is a constant for that particular problem. So when we multiply or divide all the data by any constant, all measures of position and measures of spread are multiplied or divided by that same constant. So your spreads are going to change. Standardizing into z-scores does not change the shape of the distribution. One of the cool things is the shape is still the same. But it does change the center by making the mean 0 and the spread by making the standard deviation 1. So the question becomes, well, when is a z-score big? Do you have to get 7 standard deviations above the mean before you're, awesome? Or is it less than that? So, what did I want in this blank? Something that are appropriate for distributions whose shapes. Oh, yeah. Normal models are appropriate for distributions whose shapes are unimodal and roughly symmetric. A normal model provides a measure of how extreme a z-score is. Now, with z-scores, our mean is 0, our standard deviation is 1. But for anything, if we know the mean and we know the standard deviation, there's a normal model that fits that. Okay? So the way that we write that is N stands for the normal model. This is the Greek letter mu, which stands for mean. And this is a lowercase sigma. You guys are used to the uppercase sigma, which means add them all together, the summation. But this is a lowercase, and this stands for the standard deviation. So the mean is mu, the standard deviation is sigma. One thing to be clear about, and I don't know how long it takes for this to become clear. You can all nod at this point, but it takes a while for this to kind of sink in. The mean and the standard deviation are not statistics based on a sample of data. They're part of the model, and they're called the parameters of the model. We'll talk later about taking samples. That's a whole different deal. But the way to remember it is the two S words, statistics and samples, go together, and the two P words, parameter and population, go together. If you're taking a sample of the data, then you're using statistics. You're taking a statistic. A parameter is a number that's involving the whole population. Okay? So, if we model data with a normal model and standardize them using the corresponding mean and standard deviation, we call the standardized score a z-score, and we write y minus mu over sigma. Right? It's the same thing as we did earlier.
Sorry.
Mu is the mean.
Mu is
Yeah, mu starts with M, mean starts with M. Sigma starts with S, standard deviation starts with S. That's why they chose them. Then we use this model, which is called the standard normal model or the standard normal distribution, either one. Before you try to use a normal model, you gotta check your data. If it's not unimodal and symmetric, using a normal model for that is not a good idea, because the normal model isn't going to model it very well. This is why we've been so big about, what does this shape look like? So you can check this using a histogram, is typically what we use. We can also use a normal probability plot, which we'll get to in a little bit. I don't know if we'll get to it today, but we'll get to it. So keep in mind, when we use a model, we're making certain assumptions. Whatever model we use, we will always point out those assumptions, and associated conditions in the data to make sure that those assumptions are reasonable. All right. So we were talking about how many standard deviations do you have to be above the mean to be awesome? We can use what's called the 68, 95, 99.7 rule. You're like, oh yeah, that just flows off the tongue. In a normal model, none of these numbers, by the way, are exact. About 68% of the values fall within one standard deviation of the mean. About 95 fall within 2 standard deviations of the mean, and about 99.7% fall within 3 standard deviations of the mean. So, if we apply that to SAT scores, if you were 1 standard deviation above the mean, so that would be here, that's 1 standard deviation above the mean. How much is below you? Well, this part is clearly 50%. And since 68 is within 1 standard deviation, this part is 34% approximately. So, so you're at approximately the 84th percentile if you're 1 standard deviation above the mean. You're better than 84% of the people in whatever it is that you're trying to measure.
So if you're in 86%, then it would be 2 standard deviations.
No, 2 standard deviations above the mean would be here. That would be 50 plus half of 95, which is 47.5. This is 97.5 percentile. If you're 2 standard deviations above the mean, you're a baller.
97%. And then the other one's like 99 percentile.
It's if you're 3 standard deviations above the mean, you're better than everybody except for 0.15% of the people.
Mr. Davis?
Yeah.
How did you know that from 0 to 1 standard deviation, that was 34%? How did you know that?
Oh, from within 1 standard deviation of the mean is 68%.
Oh, so
And
not-
since that's symmetric, cut that in half, that's 34.
Okay, that makes sense.
And so you just did that with a 95 too.
Right.
So you get the 47. Okay.
Yeah, that's how you got the 47.5. So if you're here, you're at, this is 68%. This is 97.5 approximately.
How's it 97?
Because this is 50, and half of 95, which is how far we need to go from here to here, is 47.5. So
Okay.
50 plus 47.5 is 97.5.
Oh, okay. I see.
Okay?
And then quick question. So
Yeah.
99.7, like why is that like the smallest range? Like that's 99%. Wouldn't that be where most of the people are?
Yes. Almost everyone falls within 3 standard deviations of the mean. So if you're talking about height, for example, about over half the people, actually over 2/3 of the people, are in the middle,
Yeah.
right? And then almost no one is more than 3 standard deviations above the mean or below the mean.
Yes.
So I don't understand what the question is then.
So like if 99.7, like wouldn't that be like the deep dark purple part? That's where most people are.
99.7 is everywhere from here to here.
Oh, so that's saying like everything?
Yeah, 99.7% of the people fall within 3 standard deviations of the mean.
Oh, okay, that makes sense now. Okay.
Okay?
Yeah.
Yeah, the 68, 95, 97, 99.7 is not percentiles. It's what percent fall within that many standard deviations of the mean.
Yes. Okay, that makes sense.
So most of the time what we say is that if you're 2 or more standard deviations above the mean or below the mean, then yeah, you are,
Star.
in a set of data, an outlier.
So then you're an outlier.
I am not an outlier.
All right, what time is this class? I don't even know. 4th period, 10:59. Oh, we got a couple minutes. So you're going to be asked to sketch a normal curve sometimes. Okay? When you sketch a normal curve, couple things to help you out. Start from the middle. it's a lot easier than anytime I start from here, mine ends up being not symmetric at all. Second thing is that even though it extends infinitely to both sides, stop drawing after about 3 standard deviations to either side. Okay? Third thing is the curve changes inflection. So if you make a curve like this, you see how it changes there from this way to this way? That's an inflection change. And you can actually, if you're paying attention, you feel it in your hand. You change from an overhand motion to an underhand motion. You feel it in your wrist. It changes.
Oh.
Yeah.
Yeah.
As soon as you feel it when there's this break and it switches, you just do this naturally. Okay? The point of inflection on this side is here, and on this side is here. It's 1 standard deviation to either side. When you sketch a normal model, what's going to go here are what is the mean, what is the mean plus 1 standard deviation here, what's the mean plus 2 standard deviations, etc. Now, there are a couple of different ways to find normal percentiles. So you can use a table, which is called a z-score table, and you will have those available to you on every test that we take and on the AP exam. You can also do it on a calculator.
Only on the numworks?
Pardon?
Only on the numworks?
No, you can do it on lots of calculators.
So mean.
It's easier on the numworks though.
I'm gonna get it. I like told myself last night to get
All
it
right.
for that.
So let's apply this to my SAT math score. All right. So the mean score was 493. The College Board, it's interesting. They report the mean scores, but they don't report the standard deviations anywhere that I could find, and I did a fair bit of research on it. I think they're hiding something.
Mm.
I hate College Board.
I don't hate them.
Oh, I don't hate them. I strongly dislike College Board.
All right. So if we want to find my z-score, it's going to be z is equal to my score, which was 600, minus 493, all over 100. So it's 107 over 100, which is 1.07. That's pretty easy to do.
So you're 1.07 above the mean.
Yeah, 1.07 standard deviations above the mean. So good, but hardly amazing.
Hard.
Not quite an outlier, but still awesome.
All right. So that's the z-score. Now, let's find the percentages. What is the percentile? So, let me give each of you one of these.
We get to keep this?
I keep these in my room. I'll run some off for you, but there's a table like that in your book. There's also that exact table, pardon me, is in Google Classroom at the top under resources. It has the tables and all the formulas.
This isn't complicated at all.
All right, so if you look at one side, you notice that the part that's shaded is below the mean. If you look at the graph at the top, right, flip it over, it's above the mean. Since my z-score is positive, we want to be on the side where we're looking above the mean.
Are we gonna? Oh, that was.
So how to find this is in the far left-hand column, find 1, and it says 1.0, and then I'm going to move over to where I get to 07. that gives you the percentile. That gives you what percent of the scores are below those.
80.8577.
56.75.
What?
What? No.
On the
Really?
opposite side, man.
8577.
I'm on the positive side.
8577.
Yes, are you looking at 1? No.
Yeah.
1. That's not 1. That's 0.1.
Which, oh, okay.
I'm 1.07, not 0.17. I'm much better than that. 0.8577.
0.8577.
So we're gonna have to memorize this?
No, you have to know how to use it.
But we have this on the test?
I've said that like 3 times now.
On the AP test?
Yes.
Yes.
Let me show you how to do it on the calculator. So I'll start with the TI.
Did you break that?
Yes, you wait for the first.
So here's what we have to do on a TI. First I have to wake mine up. And what I want to do is go to second vars, which is distribution.
Oh no. Sorry.
And then what I want,
Second what, Mr. Davis?
second vars.
Bars.
With ugly, the left of clear.
And I want to go to the normal CDF. The CDF stands for the cumulative density function.
It's weird how much these calculators can do.
So I guess I probably should have gotten out of this graph before I did it. Second vars, the normal cumulative density function. All right, so I want my lower bound to be everything to negative infinity. It's preset to -1 E99, right? That's a really big negative number. I want my upper to be 1.07 because I'm 1.07 and my mean was 0, my standard deviation is 1. Oh, that was us?
Yes, sir.
All right, well, I'll have to show the NumWorks people tomorrow. And you can see that it's 8.5769, blah, blah, blah. Those of you who have the NumWorks, see if you can figure it out by tomorrow. It's pretty easy.
Because it's NumWorks.
You do have to go not into the statistics part, but into the distribution part.
Okay.
Okay?